Today I'm going to introduce you to radical notation and show you how to simplify radicals. So first, what is a radical sign? The radical sign is the mathematical symbol that we use to communicate about roots. So some of these symbols that you may have seen before, this first one is a radical that indicates a square root, and the second one is a radical that indicates a cube root. Now there are a couple parts to a radical symbol. Usually there's some type of number underneath here. This number that's underneath here, or sometimes it's an algebraic expression, is called the radicand. The symbol itself is just called the radical. So there's usually a radicand underneath here. And then when you have this little number that's indicating what type of root you've got, this number right here is called the index. Now you'll notice that there's nothing written for the square root, and that's because square roots are so common that we just get lazy and we don't write the index down, but there's really sort of an invisible 2 here as the index to indicate it's a square root. Now, radical symbols are asking for a principal root of a number, and I'll explain what that is in a minute. And for even roots, that's the positive root. So you've seen questions like find the square roots of 16, and we know that there are 2 numbers that you can square to get 16. So there are 2 square roots of 16. But when you use the radical symbol to ask for it, that's not just asking you what the square root of 16 is, it's asking for one of those answers. And it's asking for the principal square root, and the principal square root of 16 is the positive version of that, so that's 4. If I ask what are the square roots of 4, there are actually 2 answers to that, 2 and -2, because if you square both of those numbers you get 4. But when I use the radical symbol to ask the question, which is actually read the same way, find the square root of 4, that's specifically asking for the positive root, or the principal root, so that's just the positive 2. For cube roots, we know that there's only one number that you can cube to get -27, so there's only one answer to this one, and therefore when you have the radical symbol you get the exact same answer. There's no question with odd roots what the answer is going to be. So let's practice that. These are all asking for principal roots, so the square root of 81 is asking for the positive number that you square to get 81, that's 9. The positive number that you square to get 100 is 10. The positive number that you square to get -49, there's no number that you can square to get -49, so we write not a real number here. And in this problem, when the negative is outside of the radical sign, that's actually asking you to do a 2-step process. First, figure out what the principal root of 36 is. The principal square root of 36 is 6, and then take the opposite of that. So this negative sign just comes over. For cube roots, cube root of 1000, the only way to get a positive number when you cube it is to start with a positive, and 10 times 10 times 10 is 1000, so that's positive 10. This one, -2 raised to the 3rd power, is -8, so this is -2. And this one, just like the other one, is asking you for first find the cube root of +1, which is 1, and then transfer this negative out in front, or take the opposite of it, so that's -1. Now, something interesting happens when you have square roots and you start to use variables. So let's look at that. First, with a couple of numbers. If you have the square root and then underneath that square root you have 5 squared, that means the square root, 5 squared is 25, and the principal square root of 25 is 5. For this one, when you start with a -5 down here and you square it, you also get 25. And the square root of 25, that's asking for the principal square root, so that's 5. So notice that whether I start with a positive number down here in the base or a negative number, it turns into the same answer out here. These answers are positive. And we know that mathematical symbol for something that forces an answer to be positive is the absolute value. So when we start working with variables, since we don't know whether we're starting with a positive or a negative to begin with, we have to be careful with the absolute value notation. So let's look at this one. the square root of x squared. Up here you'll notice that this index in each of these roots was a square root, and that matched the exponent underneath. So it's like the square root and the exponent, they undo each other and just leave you with the 5, or the positive or the absolute value of this negative 5. So down here, when you have a square root and a square, those are going to undo each other and just leave us with x. But we don't know if that x that we started with is positive or negative to begin with. So in order to guarantee that it's positive, I need to put absolute values around it. Same thing here, square root of 16y squared. The square root of 16 is 4, and the square root of y squared, those exponents and roots are going to undo each other and leave you with a y, but you don't know whether that y started out positive or negative, so you need to put absolute values around it. Now for cube roots, cube root of 2 cubed is the cube root of positive 8, and that's positive 2. So notice that this 2 down here in the base and this 2 right here in my final answer, those are exactly the same. And if I start with a negative 2 and I raise it to the third power, underneath that radical, the radicand is going to be negative 8, and then when I take the cube root of negative 8, I get negative 2. So when we have odd roots and exponents, we actually get the exact same thing. We don't have any examples of when it forces the answer to be positive. So as a result, we don't have to worry about absolute values when we have odd roots. So the cube root of x cubed, this index and this exponent, they're going to undo each other and just leave me with x. Here, the cube root of 125, that's actually the cube root of 5 to the third power, and then you have the m to the third power. This index is going to undo all of those exponents and just leave me with 5m. And again, because this is a cube root or an odd root, I don't have to worry about putting absolute values. Okay, one more set of examples here. So we're going to be careful about when we need to use absolute values and when we don't. So this one, 25x to the 6th, if I rewrite that as something squared, and I'm trying to do that because I have an invisible index of 2 here, 25 is 5 squared, and x to the 6th is x cubed squared. And I know that because I know that when I raise powers to another power, I multiply the exponents. Now this index and this power undo each other and just leave me with 5x cubed and no root anymore. But because this is an even root, I need to put absolute values around the variable part. Next one. Again, this is a square root, so I'm trying to get an exponent of 2 underneath here. What do I square to get 81? A 9. What do I square to get a squared? An a. And to get b to the 10th, I would need to have a b to the 5th in here. And so then the index and the power undo each other, and I get 9ab to the 5th. Again, that's an even root, so I need absolute values. Last one, cube root. So I need to have an exponent of 3 underneath. To get 8, I need 2 to the third power. To get m to the 12th, I need m to the 4th raised to the third, because 4 times 3 is 12. And then I need a p, because p to the third power is this p to the third over here. And then this index undoes that exponent, so I get 2m to the 4th p. And because this is an odd root, I do not need to put any absolute values. Let me add one thing here. If I erase this middle step here, through the magic of technology, I erase that middle step, and you look at what the exponents are in the answer right here, and right here, and right here, there's an invisible one, compared to the exponents that I started with here, you'll notice that the exponent that I end up in the answer is what you get if you divide this exponent in the radicand by the index. So 6 divided by 2 gives me 3. 10 divided by 2 gives me this exponent over here of 5. Down here, if I take this 3 right here and I divide it into these exponents on the variables, 3 goes into 12 4 times, and 3 divides into 3 1 time. So that's a shortcut you can use if you want to.